Right. So in addition to permutations, we also have what are known as combinations, which if you look at its base form, it's kind of another special type of permutation. The only thing is it's a permutation that doesn't really care about the order. Basically just meaning like when a permutation of A then B being different than B then A, in a combination, they're the exact same thing. And what that does is it changes the formula very slightly. You can see that the NCR, which is notated for combination, n factorial over n subtract r factorial, this r factorial here just helps to eliminate anything that would be a duplicate. So eliminating the fact that AB and BR or BA are the same thing, you say, oh yeah, you have A and B? Oh yeah, that's the same thing as B and A. Another notation that can sometimes be used, especially in the pre-calc side, is just an N over R within parentheses. Don't really use it a lot for foundations, but it's just something kind of fun to know. Okay. So example 1 is how many sets of 4 golf clubs should be selected from a golf bag containing 11 different clubs. So then the first question you have to ask yourself is, does the order matter? Does the order that you select these 4 golf clubs really matter? Does it matter whether you pull out the putter, then the driver, then the wedge, then the iron, or iron, then wedge, then putter, then club, or then wood? No, it doesn't. So the only thing that changes is instead of having NPR, you're just going to use the NCR. So there's a total of 11 clubs. Of course, if you're more professional, you might have more depending on different purposes, but standard set is about 11. I could be wrong on that. I don't actually golf. But 11C4 comes out as 330. So if it was some kind of rare competition, you would just have, and you could only choose 4. There'd be 330 different ways that you could select just 4 golf clubs out of a standard set of 11. Okay. A jar contains 9 blue jelly beans, 6 black jelly beans, and 5 orange. How many sets of 3 jelly beans can be selected if the selection must not contain any orange jelly beans? So this is adding a little bit of trick question. So just adding in a bit that you need to be careful. We don't want any orange. So we're not even going to consider the orange in here. We got 15 left. And we're just going to take 3. So 15C3 be 455. Now, of course, if we did them all, we got 20C3. It'd be 1,140. So of this many, of the 1,140, there'll be 455 different ways of selecting jelly beans, 3 jelly beans, where none of them are orange. Obviously, then if you subtract that 455, there'd be 685 things. I would have at least 1 jelly bean. But that's kind of just extra. So now we're going to talk about this and finding n if NC17 is the same as 20C3. Now there's a reason for it and kind of does tie along into the binomial theorem from pre-calc 30. But let's go to the formula. So the formula is n factorial over n subtract r factorial, r factorial. So on the left-hand side, we'd have n factorial over n subtract 17 factorial, 17 factorial. And it has to equal 20 factorial over 20 subtract 3 factorial, 3 factorial. Now, we can't really do anything to the left-hand side. The left-hand side would stay the exact same. But on the right side, we can simplify. We got 20 factorial over 17 factorial, 3 factorial. Now, the good news is on both of these sides, there's a 17 factorial in the denominator. So 17 factorial, multiply both sides by a 17 factorial. Those are going to be gone. So n factorial over n subtract 17 factorial equals, change my color, 20 factorial, 3 factorial. And now we kind of get to the question of asking, well, let's use some common sense here. What numbers can we do here to make them equivalent? So basically, what number subtract 17 would be the same as 3? Well, the only option would be 20. So what that's saying is that 20C17 is the same as 20C3. And if you actually type that into your calculator, 20C3, oh, we already know what it is. It's 1,140. You do the exact same thing with 17. I'm just going to type it in my calculator, just make sure, but yeah, it's 1,140. This is basically coming down to a special property that 17 and 3 add together give you 20. So that works for every single kind of combination. If you were to have, say, 9C6, it would be the exact same as 9C3. Or even if I change the numbers, 9C4 would be the same as 9C5. Right. So it's kind of a little thing that we might use a little bit later on, might not. Just going to help us with a few things. Class of 34 students need a committee of 5 students upon a fundraiser. How many different committees can be selected? So again, when you're dealing with combinations, you have to start thinking about, does the order matter? Does the way that these 5 students being selected, does it actually matter? If you can answer no, it's a combination. So all we need to do, 34C5. $278,256. And that's it. Now talk about a little bit of lottery, because some of you are going to be 18 at some point in time. And being able to purchase lotto tickets, though is not the most fruitious, it's good to know this information before you get into the adulthood and being able to gamble. In Lotto 649, you have to choose 6 integers from a set of integers from 1 to 49. How many tickets would be where you have to buy to guarantee a win? So if there's 49 numbers, it doesn't really matter whether you pick the 3, then the 17, then the 6, then the 49, then whatever numbers. It doesn't matter the order that you pick the numbers, because they're going to be put in sequential order anyways. So if your numbers are 3, 17, 49, 16, 4, and 1, these numbers are going to be put in order no matter when you do it. So 49, C, 6. There would be, I'm doing my math right, yeah, 13,983,816. So there would be that many unique tickets. And of course, you do get prizes depending on whether you get 4 numbers correct or 5 numbers or all 6. But if you're going for just grand prize, you would need to buy almost 14 million tickets. Now, my extension that I love doing is talking about what's the cost. If you want to guarantee your win, I believe that the tickets are all $5 a piece. So you take that 13 million, multiplied by 5, it's almost $70 million that you'd have to spend. It could be 5, it could be, I don't actually buy lottery tickets very often, so I don't actually know. Last thing I heard though is that the max jackpot is only like 50, so you'll be 20 million in the hole if you were to somehow get a loan for that amount. Okay. So we go on to further and more complex things. So for example, having several sets. If there's 12 boys and 8 girls in a math club, how many ways can a committee of 3 boys and 2 girls be formed? The reason I chose these numbers is because it's nice and proportional. 3 times 4 is 12, 2 times 4 is 8, so it's proportional. This ties directly back to the fundamental counting principle. How many options do you have for one thing multiplied by how many options do you have for the other? Well, out of the boys, it'd be 12C3. That would tell us how many options we could get a committee of just 3 boys. And you type that into your calculator, it comes out as 220. Well, for the girls, it'd be 8C2, because that's how many options it would be to get 2 girls on this team. And that works out as 28. And by that fundamental accounting principle, we're just multiplying our options. Every 6,160 different committees that could be formed. How about a 10-card hand that you need 3 hearts, 4 clubs, 2 diamonds, and 1 spade? I'm going to take for granted that you know a little bit about cards. So out of curiosity, you can talk about hearts. For some reason, I always love drawing these. Make that look a little more clubby. Fill in the heart. Sorry, I'm actually taking up time. And we have diamonds. And finally, our spade. If you play any cards, you should know that there's 13 of every single suit. There's 4 suits. So for the hearts, there's 13 hearts. We have to have a group of 3 of them. Doesn't matter whether we have the ace, the 7, and the 9, or 7, have the 9, 7, and the ace. The order doesn't matter for that. And then 13C4 for the clubs, 13C2 for the diamonds, and 13C1 for the spades. (13C3), 286, 13C4, 715, 13C2, 78, and 13C1 is 13. So if you take 286 multiplied by 715 multiplied by 78 multiplied by 18 or by 13, sorry, we get 207,352,860 different 10-card hands. Because that's 3 hearts, 4 clubs, 2 diamonds, and 1 spade is all 10 cards that we would need. Hence why people playing cards, it's quite a big deal to get a good card hand. You can talk about, actually we'll talk about poker later on as well. Again, might as well expose you and let you have an understanding of what it actually means with different card games and such. Obviously, I'm not going to encourage you to gamble or use money, but they're good mathematical games to talk about chance and probability and all that kind of idea. Okay, just before we get to the poker though, if 2 letters are chosen from the word who and 3 letters are chosen from the word cares, how many 5-letter arrangements can be formed? Well, there's 3 letters in who, we're going to take 2, and there are 5 letters in cares, and we're going to take 3. So 3C2 should be 3 if I'm doing my math right in my head. Yep. And 5C3 I think should be 15. I could be totally wrong. No, it's 10. Yeah. Yes, absolutely. I love keeping this question because who cares? Okay, go back to poker. One of a favorable 5-card poker hand is a 3 of a kind, which means you have 3 cards of one value, a 4th card of a second value, and a 5th card of third value. How many ways can you be dealt 3 of a kind? So here's the deal. First off, to get a 3 of a kind, we need to have 3 of the exact same kind of card. So we have to have 3, actually I won't use 4s, 3 kings. But after that, we'd have to have 1 of something else and 1 that's not a king or whatever that is. If it's the same as what this is, then you have a full house and you have considerably better card than just a 3 of a kind. So if we're talking about just kings, how many kings are in a deck? Hopefully you're able to answer that there's 4. Now it doesn't matter whether you have the spades, clubs, and the hearts, or you have clubs, hearts, spades. It doesn't really matter because that's why we're going to use about combination. Now we're going to have to multiply it by something else. We have to have something else here. So in total, we know that there's 52 cards in a deck. It doesn't matter what this card is, but it just can't be a king, which means out of the 52 cards, we'd have 48 cards left in the deck to choose from. It doesn't matter which one it is, it has to be one of those 48. So 48C1. But the last card can't be a king. It can't be whatever one of these are, which means we'd have 44 cards left to make this option. 44C1. Now 4C3, I should be able to do this one in my head. It should be 4. Okay. 48C1 is 48, and 44C1 is 44. So when you multiply it together, there'll be 8,448 different ways of getting a 3 of a kind. If we're looking about again, this is just an extension, the total amount of 5-card hands that we could have would be 52C3. And 52C3 will be 22,100. Which, in all grand scheme of things, a 3 of a kind, sorry, no, 5C3, sorry, I need 5C5, 52C5, sorry. What am I doing? Rather than a 5-card hand, there'd be 2,598,960. So if you look at the proportion of a 3-card hand versus the total, or 3 of a kind versus total, we're looking at, well, oh, okay, hold on. Aha, I knew that there's something off with this. I apologize. This is still our total for 5-card hands. The only issue with this is that we could have king. So this would just be basically the way of having 3 kings. 4 times 48 times 44. But the problem with this is we could have kings, queens, jacks, 10s, or anything. So we'd actually have to then take our answer and multiply it by 13. I am sorry, guys. There. That makes more sense. Makes the 3 of kind a little bit less rare, but it's still a very small proportion of this total amount that could be a 3-card hand, or sorry, a 3 of a kind. And the next example. So, if by chance we had a class that had 6 females and 6 males for graduation, and principal wants to just meet with a group of 5, how many selections are possible? So this question just talked about the total. So we'd have 12C5. 12C5. There'd be 792 different selections. Again, the reason we're talking about this doesn't matter whether you take student 1 or student 2 first. They're still going to be part of this group to discuss grad. Now, if by chance we had to make it uneven, and if the group has to have 2 females and 3 males, out of the females, we'd be choosing 2 of them, and out of the males, we're choosing 3. So 6C2 is 15, 6C3 is 20. So out of this 792 different selections, there'd be 300 of them that would have 2 females and 3 males. Now, if one of the females was called, say, Yennefer, I don't know, sounds like a fun name. How many 5-member selection committees must have Yennefer? 1 other female and 3 males. So that just means that this total amount of 6 females is going to be dropped down to 5. And since Yennefer has to be in here, she's taken out of the 2 possible females. So 5C1, there'd still be 3 males being taken out of the 6. So 5 times 20 be 100. So out of these 300, which have 2 females and 3 males, 100 of them would have Yennefer in it. How about talking about physics or any kind of multiple choice type idea? Sherry's writing a physics exam. Every so often I have old friends put into my stuff. Instructions say that she must answer a specified number of questions for each section. How many different selections are possible if she has to answer 2 of the 4 questions from part A and 3 of the 5 questions from part B. So if there's a total of 4 questions in part A, she has to choose 2 for C2, which comes out as 6. Now if we have to answer 3 of the 5, 5C3. C3 is 10, which comes out as 60. Now the question changes that if she has to, she must answer 2 of the 4 questions in part A, and at least 4 of the 5 questions from part B, our question changes. Because she still has to answer 2 of the 4 from part A. But if she has to answer 4 questions from part B, 4C2 times 5C4. Let's see, this is 6, that should be 5. There'd be 30 different ways of having 2 from part A and 4 from part B. Then we have to consider the fact that, what about if she answers all 5 questions from part B? Which just be 4C2 multiplied by 5C5. 4C2 is 6, 5C5 is 1. So 30 plus 6 is 36. Now we get into kind of the harder nitty-gritty stuff. So I'm going to get into that form, understanding that the combinations are n factorial over n subtract r factorial, where the n is just whatever this is on the left-hand side of the C, and the r is just whatever's on the right-hand side. So if we have a question like this, it would look, this is going to look like an n factorial over n subtract 5 factorial. Now, that will be the entire thing in the numerator, whereas the entire part in the denominator would be an n subtract 1 factorial over an n subtract 1 or n subtract 1 subtracting 3 factorial. Oh, I forgot about the 5 factorial up here, and I forgot about the 3 factorial here. All right, so good news is we have a fraction within fractions. The other good news is you've had lots of practice with me with fractions, so how do you divide fractions? You multiply by the reciprocal. So meaning the first fraction, the numerator, is going to stay the exact same. N factorial over n subtract 5 factorial. 5 factorial. You're going to multiply by the reciprocal of here. So instead of n subtract 1 over, that n subtract 1 factorial is going to be on the bottom. Whereas the n, and I'm going to just simply combine this -1 and -4, or -3, be a -4, just in one step. Saves me a little bit of extra room, little bit of work. Now, further here, it kind of goes down to a little bit of common sense. Now, as I've said before, it works out really nicely to just start with your bigger number. Well, in here, we have 4 different things. Oh, I forgot a factorial here. We have 4 different things that are bigger things. Well, if you start with your biggest, which is n, it's going to actually be very useful. Because n factorial is n times n subtract 1 times n subtract 2. Oh, automatically we can see that we're going to be able to cancel things off. Because in the other fraction, we have this n subtract 1 factorial. So that allows us to cancel a numerator and a denominator off right away here. Now, if we compare, so then we just have an n left on the left-hand side here, on that left fraction. If we compare an n subtract 5 and an n subtract 4, our bigger number would be that n subtract 4. So 1 less than n subtract 4 would just be n subtract 5. And that's exactly what we're going to try and cancel off there. So we have the n subtract 5. And those ones are going to cancel off. Now we can't forget about the 5 factorial and the 3 factorial. But once again, we're going to start with our bigger number. 5 is bigger. 5 times 4 times 3. Oh, it would be, we could continue 3, 2, 1. But 3 factorial is all that we're going to have to go down to. Because a 3 factorial and a 3 factorial cancel off. So we would be left with an n subtract 4, and a 5 times 4. To further simplify, it's going to be really nice. N times n subtract 4, just be an n squared subtract 4n. And 5 times 4 is 20. So that's everything that we have there. And that is as simplified as that one's going to get. Whereas in our other one, we're going to actually do some solving. So I'm just going to completely split it off. Once again, keeping in mind what our form is. We have 2 multiplied by nc2. So we'd have an n factorial, n subtract 2 factorial, 2 factorial equals an n plus 1 factorial over an n plus 1 subtract 3 factorial, 3 factorial. Before we go into anything too intense, let's simplify what we can. The first I'm going to suggest is the fact that 2 is the same as 2 over 1. And 2 factorial is just 2 times 1, which really means a 2 in the numerator and 2 in the denominator cancel off, and that one's gone. N factorial over n subtract 2 factorial equals n plus 1 factorial. Combining the plus 1 and subtract 3 will be a negative 2 factorial, 3 factorial. Last but not least, let's do some fun stuff here. See, we can see that in our denominators here, we have an n subtract 2 factorial. So if we multiply both sides by an n subtract 2 factorial, because whatever you do to one side, if you do to the other, it still maintains equality. But it also means that they can be completely gone. So we'd have an n factorial. There'd be, of course, you could put a 1 in your denominator, but it's not going to change anything. N plus 1 factorial over 3 factorial. Now I'm just going to simplify 3 factorial as 3 times 2 times 1, which works out as 6. Now, just like we did here, and as we've done in previous years, really you don't want to deal with fractions as long as you can get rid of them. So we're going to just multiply both sides by 6. So we're going to have a 6 n factorial equaling an n plus 1 factorial. And let's further simplify. The bigger number between n and n plus 1 would be n plus 1. So 6 n factorial, n plus 1. 1 lower than n plus 1 would just be n. And that's all that we're going to go to. Because if we divide both sides by n factorial, again, that's maintaining that equality. They're gone. We'd have 6 equal to n plus 1. Subtract the 1. And n equals 5. So we go back and check. If you take 2 and multiply it by 5c2. So first off, 5c2 is 10. So 2 times 10 is 20. And if you plug a 5 into here, you get a 6c3 and 6c3. is also 20. So our final answer of n equals 5 is all there is to it. Alrighty, so we'll have some fun.